We saw that language is complex. There is no single meaning, we disagree on the grammar, and there is some ambiguity. There is also not a set of definitive sentences because we are creating new sentences and new language every day. Instead of talking about one single meaning of a sentence, we're going to talk about a probability distribution over meanings, which takes us to the topic of language models, which is an approximation of language. The aim is, of course, to model natural language. This is what we want to do to be able to use it in different natural language processing tasks. Consider this sentence. Did you call your... Is it possible to guess or predict the next word? Possible words could be mother. Did you call your mother? Or did you call your doctor? Or did you call your child? Unlikely words would be something like, did you call your dinosaur? Or did you call your oven or your fridge? What we want to do when we build the model for natural language is to actually estimate the probability of all the words PW given the sentence we have, did you call your? Okay, for any W, we want to be able to estimate this from data. Ultimately, the goal of building a language model is to build a probabilistic language model that assigns a probability to each next possible word, that is, predict the next word. For example, what is the probability of mother given that the sentence is did you call your, given the sentence, probability of dinosaur given the sentence, probability of doctor given the sentence. Okay, so you want to be able to predict the next word. We want to be able also to use these language models to assess the probability of a sentence or a sequence of words. For example, predict the probability to see this sentence in the text. What is the probability of open your book on page 6 versus the probability of book open 10 you're on page. So we see that one sentence makes sense, the other one doesn't make sense. And we hope that the probability of the sentence that makes sense would be higher than the probability of nonsensical sentences. Language models are crucial in many natural language processing applications, and these include spell correction. For example, given the sentence once upon a time versus once upon a time, given a large corpus of text, we will build a language model based on this text, and we hope that the probability of once upon a time would be much higher than the probability of once upon a time, which will help check the spelling in text. Statistical machine translation used by excellence language models. Given some sentence to translate, we have few possibilities, such as in this example, out of sight, out of mind, with the two possible translations, one of them being the correct one. So we could calculate the probability or estimate the probability given a large corpus of text using the language model, and hence we could estimate that what would be the best translations for this sentence. We use also language models to seek information, such as doing text classification, information retrieval, and information extraction, and also for speech recognition, language identification, text summarization, etc. So what's the idea of language models using n-gram models? Suppose we want to estimate the probability of the word page following the sentence, open your book on. In other words, we want to estimate the probability of page given that the sentence observed or the history is open your book on. Before we dive into n-gram models, let's first examine how we can estimate the conditional probability of having a word or the prediction of a word given a sentence. For example, the probability of the word page, given that the sentence is open your book on, we could use the frequencies in a large corpus of text to estimate this probability. For example, probability of page given the sentence open your book on could be the ratio between the count or the frequency of the sentence open your book on page divided by the count of open your book on. So if we have these counts and assuming a very large corpus or very large text, we could estimate the probability this way. If you want to estimate the probability of the sentence open your book on page, then we are going to use the frequencies again in the large corpus by doing the ratio between the count of the number of time the sentence open your book on page appears in the corpus divided by the count or the frequency of the number of sentences that has 5 words. All right, so we assume that we have a very, very large corpus of text that we use to estimate these probabilities. However, this might lead to a poor model because many sentences will have a probability of 0 and does not appear enough in the corpus to be actually estimated, for the probability to be estimated properly. The main problem is how to estimate the probability of a sequence of words. In other words, how to estimate the joint probability of having the word W1, W2, Wn. So we assume that our sentence is made of a sequence of words, Wn, and we want to be able to estimate this joint probability in the text. One possible solution is to decompose the joint probability using the chain rule of probability. That is, the probability of the sentence or the word W1, the sequence W1, Wn, is the probability of the word W1 times the probability of W2 given W1 times the probability of W3 given W1, W2, etc. So I'm going to use for each time the probability of the word given the history or the sequence of word that came before this word. Okay, so this is a known result in probability. So I'm going to use this chain rule that we could generalize and write as the probability of the sequence of words W1, Wn is the product of the probabilities of the word Wk, from k going from, this should be k actually, from k going from 1 to n, of Wk given the sequence of words happening before Wk. Okay, so I'm going to use this trick to be able to do this estimation. The idea of the n-gram models is to, instead of using the whole chain, let's just approximate it by using the last words. For example, for what we call the bigram models, we're going to use the Markov assumption that each word will depend on the previous word. In other words, we're going to use the probability of Wn given the previous word Wn minus 1 to approximate the probability of Wn given the sequence of words that happened before Wn. For example, if I had the probability of page given the sentence I had, I could approximate that by the probability of page given the word that just happened before, which is on. Open your book on, page, so the probability of the page would only depend on the previous word on. We could also talk about what we call trigram models or 3-gram models, where we look not only at the previous word, but at the 2 previous words in the past, or the n-gram models more generally that look at the n-1 words in the past. So we could go in the past, like looking at the context of what just happened, either by 1, 2, or more words. Given this idea, the conditional probability of the word Wn given the sequence of word W1, W2, Wn minus 1 will be then equal to or approximated by the probability of Wn given the sequence of word just at the n level, which means that we are going just to take the n, big N, previous words in the sentence. So Wn given Wn minus 1 plus 1 up till Wn minus 1. So these assumptions will simplify the computations of the probabilities and specifically the estimations from large amounts of data. So if we want to calculate the probability of a complete sentence using, for example, a bigram, we're going to write this as PW1Wn will be approximated by the product of the probabilities that look only at the previous word. In other words, it's going to be the product of k going from 1 to n of the product of the conditional probability of Wk given the previous word Wk minus 1. Now, how do we calculate the probability of a word given the previous word or the previous words? We're going to use maximum likelihood estimate to do that. So probability of a word given the previous word will be estimated by the count or the frequency of the sequence Wn minus 1 Wn over all the count over all the sequences Wn minus 1 W for each possible word. This can be simplified as the count of Wn minus 1 because this actually just means that look at all occurrences in which Wn minus 1 occurs followed by any word W. So this is simply the count of Wn minus 1. Okay, this is a way to estimate these conditional probabilities. N-grams capture in general syntactic dependencies between the words. For example, bigrams would capture the syntactic dependency that a noun comes after a verb, or that a verb comes after the word to, etc. But in practice, bigrams are not enough. We like to use 3 or more grams, 3 grams or 4 grams or even 5 grams. We also use log probability to get a larger numbers than probability between 0 and 1, and we can always go back to the original probability.